Yeah, so I'm going to talk primarily about finite state automata. All of you had a course in automata theory? Did all of you have a course? Okay, so then you remember what is a finite state automata? What is a finite state automata? It's a phi tuple. Q. F. Okay, and if this is A, then L of A, all those strings in sigma star such that W and these languages are called regular languages. What are examples of regular languages? Standard examples. Can you give me some? Some examples. Some examples of regular languages. Sigma star. Okay. Then some you might have done in class. Yeah. Yes, star B. Right. And then you know that it is closed under union, intersection, complementation, then some more. Yes, so this is fine. So what I'm going to do today is, the idea is that once you do a course in automata theory, you have this strict notion, or you have an emerging notion that this is too weak to accept certain non-regular languages. So can you give me some non-regular languages? A power n, B n, A power n, B power n. Then A power P for primes, right? A power n factorial, number of A equal to number of B. So then you see that it can't accept pretty much anything non-linear, right? Yeah, so what we are going to do today is, we'll do some examples. For instance, this is an exercise question for you actually. It was an exercise question. So half of L, which is x such that there exists y in sigma star, length of x equal to length of y, and x dot y is in L. Right? You collect all the strings in L, you take only the first halves. That's going to be half. Okay, so let's denote it by half. Now let's generalize this a bit. N by m of L for some n and m. X says that instead of this it will be size of x, n times size of x will be no, size of y. So in that case m times size of x will be just a crude generalization, right? In that case it will be, yeah, or you have to write it some other way. Yeah. Oh no, sorry, size of xy, right? Because in that case half of x will be half of xy. So let's call it rationals. Now what about square? No, log of L. X is that there exists y in sigma star such that size of 2 power size of x will be size of x. Log L x is that 2 power size of x is size of x. All right, so that's for exponentials. What about polynomials? Square. There are many definitions of square root, so I'm just calling this a square root of n. X is that mod x square. So in general, any polynomials. Here you can replace size of xy as any polynomials over length of x. Okay, then fourth, just Fibonacci of L. Size of x is that, there x is y, is that size of xy will be nth Fibonacci number. I mean, so you take the size of x, you find that Fibonacci number, and xy should be there. You'll saw that all these are regular. And this completely blows your mind actually, because the all functions there are non-linear. And this actually tells you that okay, it's not the case that it's always non-linear. Okay, so first we will start by this. There is a standard way. This is a standard homework problem. There is a standard way to solve it. We'll solve it using the standard way, but then that can be generalized to others. So then we will show an easier technique, and then we'll solve the rest. Okay, so for solving this, so let's revisit that determinization of finite state automata. So finite state automata, you can draw like this, a graph. Are you following this? If you have any doubt, just ask me. So you have a graph. Suppose this is non-deterministic. Then if I give you a string, A1, A2 to AN, and ask you to find out if there is a run from some Q0 to Qn and F, the problem arises because you don't know which path to take, right? So you will have to find all paths of this length and then check that if you reach some Qn. So there is a standard determinization, and you remember the proof? Standard way to determinize a finite state automata? Subset construction? Yeah? Yeah, so there is a standard way. Let's do this time, just informally. Suppose I have a collection of pebbles, okay? Just some pebbles. What you can do is that you can take pebbles and put it in the states. So I'm going to check if it has a path which leads to a final state in just exactly n steps. Okay, and that algorithm we can formulate it as a subset construction. So how do I do that? So I have some pebbles. At present I don't know the number because I have an infinite collection. Later we will show that you don't need actually an infinite collection of pebbles, you just need finitely many. Okay? So I take one pebble and put it in the initial state. Okay? Then I see A1. What do? What I do is I look at all the states which are holding the pebbles, see A1, then take this pebble, and where all I can go from a pebble state, where a pebble is there, where all I can go from A1, I put a pebbles there. I put pebbles there. Okay. Because I have an infinite collection of pebbles, I can just take one, put three back. Right? But at any point of time, I don't need more than n pebbles because there are only n states. Right? So I just need n pebbles. I just need n pebbles. So what's our algorithm? Put all the pebbles in initial state. Whenever I see A1, whenever I see a letter AI, put pebbles in those states which are reachable from a pebble state on AI, take out all the rest of the pebbles and continue this. Finally, once you finish the state, finish reading the string, you check if there is a pebble in a final state. Right? So this is exactly the subset construction. Why? Because now the pebbles can be represented as a subset. Right? At any point of time, there are pebbles, states with pebbles and state without pebbles. So I'll collect all states with the pebbles, and that I'll call a subset. So what will be the? So if the automata is just Q, sigma, delta, just say I. It's much easier because F is anyway a subset. So why not I also a subset? So what is my algorithm? My automata which simulates this procedure will be a DIT. Okay. So what will be the state set? All configurations, all pebble configurations. So that will be that I can represent as power sets. Right? Initially, I put my pebbles as in I, all my pebbles in I, and this is again sigma. And then delta dit is there, then F. This will be any subset F prime superset intersection such that F prime intersection F is non-empty. And what will be delta? Will be what? A subset S of Q will be what? A will be what? This is standard subset construction, so you should tell me. Yeah? Delta of S comma A. All right. So this is fine. So now let's solve this using the same technique, half. What is suppose our financial automata looks like this. Okay. Now I'm going to read a word X, A1 to AN. Okay. Now I need to accept this word if there is some string Y, B1, B2 up to Bn, such that what? A1 to AN dot such that B1 to Bn is in L. Right? Clear? So this is Q0, this is QF. This is same as saying that there is a run from Q0 on this string W, X dot Y, to some Qn in F. Right? This is same as saying there is some state P such that Q0 takes X to P and X takes Q0 to P, Y takes P to Qn. Right? Right? Now, suppose I have 3 pebbles. But this time I have them colored. Red, green, yellow. sorry, blue. How do I do it? All I need to check is that I'll get a string X. Okay. I have to verify that there is a string Y such that X will take from Q0 to P and Y will take P to Qn. Okay. Any ideas? Okay, I'll give you an example. I'll give you some starter. Suppose I put my red pebble here, okay, and my green and blue here, some state, okay, green and blue here, some state. Now I start reading A1 to AN. Okay. How do I verify this condition that there is some Y such that it reaches this? How do I verify these conditions? I start with my red pebble in the initial state, green and blue in some state. I put them together. Now, okay, I'll give further more information. When I read a string A1, I'll take the, first of all, let's assume that this is deterministic finite state automata, so we don't have to worry about too much things. Okay. When I read A1, I'll take the red and I'll go to some state which has an A1 transition. At the same time, I'll take the blue and go to some state which has a transition and not necessarily any letter. I don't know, I don't prescribe any letter. Any letter is fine. I'll take my blue here, but I keep the green the same. Now what's the idea? Yeah? Yeah? Exactly, right? Is it clear? So what he said is the following. Okay. So you start with red pebble in the initial state, green and blue in the same state. Okay. When you read the string, you make transitions on the red pebble one by one, A1 to AN. At the same time, you keep on moving the blue pebble, but keep the green pebble there. Why? Because we want to make sure that wherever X is going to finish the run, that's exactly the same place where Y actually took off from, right? And finally you verify that red reaches the state where green pebble was and blue reaches a final state. In that case, and since we are making transitions of the same kind, of the same length at every state, whenever we make a transition for the X, we make a transition for Y. So they are of the same length. The fact that red and green are in the same pebble ensures that they end in the same state. And finally, blue ends in final state implies that this run ends in a final state. Right? So now how do you formalize this? Just like here. What will be the states? So this is Q, sigma, delta, Q0 and F. So what will be the automaton for half A? Some name. What will be the automaton? What will be the states at Q prime? Sigma, delta prime, I prime, and F prime. What will be Q prime? Yeah? Yes. Right? All three tuples on Q. Because there is an order tuple because they maintain the order. You can assume an arbitrary order, red, green, blue. Now, this first component shows where is the red pebble, second component shows where is the green pebble, third component shows where is the blue pebble. What are the transitions? Delta prime. Okay, so PQR on some AI goes to some P prime, Q prime, R prime. If then what is P prime? What are the relationship between these things? P prime will be delta of P and A. Q prime will be, this is a green pebble, so we keep it fixed. So what is Q prime? Q. What is R? What is R? Delta of R comma some B. For some B, because we don't necessarily care about the transition, right? And what is the initial state? What, how does the initial state look like? Set of all PQRs is that. So is that. First of all, it's element of Q. So is that. What is the relationship between PQR? P belongs to I. Q is capital Q minus I. Pardon me? Yes. Why? Because you don't necessarily need to place it in a non-initial state. So P element of R and Q equal to R, right? What is F prime? P intersection Q is? What is P intersection Q? Yeah, but P is just a state. So you mean to say P equal to Q, right? P equal to Q and R is in the final state. Right. Now how do we prove this? This is not a proof, right? This is not a proof. So it's enough to give me an argument, but do you know how to prove these things? It's not a formal proof, right? For a formal proof, you need to argue that if a string xy is accepted here, x is accepted here. And if x is accepted here, then there is some y with the same length that is accepted by these automata. Right? How do you prove this? So one standard way in proving all these things, for instance, this, you used to use induction, right? And instead of saying that there is a, so you will say that, okay, if there is any run, then you can simulate half of that run in this machine. Okay. Yeah, but it is clear that it somehow simulates this. Right? So this is with 3 pebbles. Now let's do a slightly different way. This thing, okay, this pebble stuff, and then we will move on to the general technique. Okay, this time our approach is slightly different. Can you see any other way in which we can do this? At present, I only provided you 3 pebbles. Suppose I give you only 1 pebble. Okay, I'll give you only 1 colored pebble, 1 white pebble, and all of them black pebbles. Suppose you have this finite state automata. What you have is 1 white pebble and rest of them black pebbles, lot of them. But we know that you don't need more than n pebbles because there are only finitely many states. Here what we did is that we started the run from x also went forward. We started an arbitrary point, y also went forward, right? And finally we checked that we meet where y started from and y reached final state. Can you think of some other way? For instance, you go forward, x goes forward, and y comes backward. Can we think of?
Do something like both white and black are in the start state. Read 2 characters, black moves 2 places and white moves 1 place.
Yeah. Okay.
And when black reaches final state, white will be somewhere.
Yes, but in that case we won't preserve this property, right? X has to finish where Y has to begin, right? It's not necessarily that it's not enough that the length of the string is just double, right? Yeah, but necessarily you have the correct idea. Exactly, go backwards, right? So what do? You have initial state, okay, and then you have final states. You place the white pebble here and put black pebbles in all the final states. Now what do? When I read an AI, what do?
Any of these final states, all of these final states randomly to some state.
Yeah.
And keep putting the white ones. And if you're able to read by the time you've finished A and white and black are in the same, then
Yes. Is it clear? What he said is the following. When I read A1, A2 to AN, what do? I keep on moving the white pebble forward. At the same time, I take the black pebble and I move backwards. I don't take transitions forward, I take transition backwards. Nobody actually restricts me to take transition backwards. So formally what is it? So given a subset S of Q, I can define backward set of S as all states P such that there is an A in sigma such that delta of PA is in S, right? This is the set from which I can reach the set S on some transition. Is it clear? B of S will be all those states P such that from P I can reach a state in S, right? Now the same construction, how do I formally write this construction? What is Q prime? Yeah, louder.
How are we ensuring that suppose X reaches some final state?
Yeah.
And it is not but in this case we are starting black from the final state.
Yes.
But it doesn't ensure that X is reaching that state where Y started. Means we're telling
No, we don't ensure that Y started. We are coming backwards. So all we need to check is that X reaches a place where there is a black pebble, right? Because nobody actually tells you that you have to accept guess the Y in the same order. We are actually guessing Y in the reverse order, right? So the idea is that white pebble will move from A1, A2, etc. And the black pebbles will guess Bn minus 1, Bn minus 2. And finally, when it reaches the middle, when they meet, we check that white pebble reaches a place where a black pebble is, right? And by the construction, we can ensure that there is a string of length size of X which reaches a final state, right? Clear? Right? Yeah, now how do we write this formally? Q prime. What is Q prime? You want to try? Okay. What is Q prime? Yeah, it's a tuple. Yeah, but what exactly is it here? It's an ordered tuple. We know that. All you need to remember is where the white pebble is and where the black pebbles are, right? And where the white pebble is a single state, right? Because it is a deterministic automaton. And there is only one white pebble, so it's just one state. And black pebbles can be in any subset. So what is Q prime? Q cross 2 to the power Q. Good. And delta prime will be given a state P and a subset S, we can go to Q and a subset T if you can move a white pebble from P to Q And you can take back all the move all black pebbles from S to T when, yeah, P delta of P comma A equal to Q, and make use of this definition. B of S. B of S, make use of this. What is the relationship between S and T? B of S equal to T. Is it clear? Is it clear? Is it clear? What is initial state I prime? What is initial state I prime? I comma F. And final state F prime. Such that, clear? Is it clear? Right? We read only A1 to N, right? We read only X all the time, because the definition is that we get only X, we get the Y, right? So we simulate the Y, right? So this is fine. Now if you try too much, if you try a bit hard, you may be able to come up with similar constructions for this, but then it doesn't still help you with any of the rest. It's a bit harder. So that's where something else helps really. You don't have to go through all these pains, These are in some sense tricky. Okay, so what I'm going to do is, it's again another nice things, right? Because finite state automata are labeled graphs, right? Labeled directed graphs. And there are standard, and you can see these are standard graph properties, all represented as simple path properties on graphs. So you can actually compute them much easier. Okay, so let's look at this delta. There is a standard way to represent this delta. The standard way in which you do it is by listing all the transitions. Another standard method which is used all the time in graph theory is adjacency matrix. What is adjacency matrix in terms of a finite state automata? It is a Boolean matrix. Don't get scared. This is all very simple stuff. What I'm going to talk is very simple. Boolean matrix, matrices of dimension Q by Q. For the moment, let's ignore the labels. So what will be this? So we can represent delta will be a matrix Q by Q such that this is 1, sorry. This is 1 if there is some transition from P to Q, because it's a directed graph. So at the adjacency matrix, it can be symmetric. So you say that PQ is, the entry is PQ is 1 if there is a transition from P to Q. Otherwise it will be 0. Okay. Should have used small letters, sorry. Right? If it is 0, it means that there is no transition. And these are Boolean matrices. because you have only entry 0 and 1. So this is for delta. And what about delta A? What will be the natural definition of delta A? You have the entry PQ is 1 if, yeah, if there is an A transition from P to Q, otherwise it will be 0. Okay. Now, so let's, what is, you have done a course in graph algorithms also, algorithms also. What is Floyd-Warshall algorithm? Yeah? All pairs shortest path. And what do you do in that? Yes. So if you have a relation, suppose I am given delta. Okay. Let me define delta 0 as I. Okay. The identity matrix. So what does delta 0 says? Delta 0 says that okay, PQ as an PQ is 1 if and only if P equal to Q. The delta 1 equal to 1 obviously. What will be delta square? Delta dot delta. Remember when we multiply, we follow Boolean multiplication. 1 dot 1 is 1 again. 1 plus 1 is again 1. Okay. So what is delta dot delta? Okay. So we have a column here of P, and we have a column here, we have a row here of P, and we have a column here of Q, right? And what will be the element PQ? PQ will be this summation, right? This dot this plus this dot this plus this, so on. What exactly actually delta square computes? So PQ, delta square of PQ equal to 1 if exactly. Delta square PQ is 1 if there is, first of all, if there is a case such that PK is 1 in here and KQ is 1 in here, right? That means that there is a 2 path or walk, because rather we will use path only, because in graphs it's path, in walks and in automata it's always paths, right? If there is a path of length 2 in the automaton A, right? So in general, I claim that delta I of PQ is 1 if there is a path, so this is a lemma, there is a path from P to Q of length I. How do we prove this? Yeah, this is proved using induction. But just recount what are the arguments. First of all, you know that delta 0 is true. Delta is also, you can take it for granted. This can be the base case. Delta can be the base case. So you will assume that, so delta I plus 1, you have to show that there is a delta I plus 1 PQ is 1 if there is a path from P to Q of length I plus 1. Now what will be the inductive step? This will be the inductive step, but what is the argument? Where do you use induction hypothesis? Yeah? Yeah, so it will be delta I dot delta, right? Now you can apply induction hypothesis here and induction hypothesis here, right? In this you will say that this is 1 if there is a case such that delta power I of Pk is 1 and delta of Kq is 1, right? Now from the inductive hypothesis you will get that delta power I Pk is 1. Should I write it? It's very simple, that's why I am not writing it. delta power I of p comma k is 1 if and only if there is a path of length k from p to q, or path of length I from p to q. And hence you can compose that path with the path you get from this, which is k to q. You will get that delta power I plus 1 of pq is 1 if and only if there is a path. Clear? Right. So let's so that's for general adjacency matrix, right? You know that if you take the adjacency matrix and multiply it again and again, you will get for arbitrary paths. Very standard. Now I'll say that delta power w will be, suppose w is equal to a1 to an. Delta power w is delta power a1, delta power a2, delta power an. And then I claim that delta power w of p comma q is 1 if p goes to q on w. Is it also clear? Remember, how do we define delta A for A element of sigma? You take, this is going to be just superposition of all these matrices, right? This one, right? Just add them all up. This one. If you add all of them, you will get this. Now I claim that in order to find where, so this collects all runs in an automaton on W. See that? This collects which all state goes to which all state on W. You just multiply all the transition matrices, the adjacency matrices of these labels. Now how do we prove this? Yeah, you are saying induction. What about somebody else? How do we prove it using induction? Do you see that, or should I do it? It's fine. The idea is that you will again argue by induction. For the base case, you know that delta A is, in delta A PQ is 1 if and only if there is a one path. Now you argue by induction. Suppose the size of the word is of, if the size of the word is at most n, you assume that this is true. Okay. Now for a word of size n plus 1, you can write it as a1 to an dot an plus 1. And for this a1 to an, you assume that by induction hypothesis, this is 1 if and only if p goes to q on w. And delta of w in that case can be written as this dot delta of a n plus 1. Right. Now you use the same technique. You say that, okay, this is 1 if and only if by multiplication rules you have two positions. There is a case is that this is 1 and this is 1. So, right? Okay, this is fine. Yeah, so what does it do? It just collects all the runs. Okay. Now let's use it for solving our half of L first. Okay. So what do? I'm just going to give you some, first of all I'm going to give you the definition right away. Suppose this is our automata and for which we want to find the half of L. Okay. Now my new automaton will be q prime sigma delta q0 and f. Okay. Sorry, delta prime q0 I prime and f prime. And what will be my q, and these adjacency matrices I'm going to, okay, q prime comma m q cross q. Okay, I'm going to represent as all these adjacency matrices. I'm going to represent as a m q q, which means that all Boolean matrices of this dimension. Okay. Now, what do? What is my delta prime? What is my delta prime? On p comma a, on ai, I goes to q, such that q is equal to delta of p comma ai. More importantly, what do I do with the a? I just multiply it with delta. Okay. what is the initial state? I say the initial state is P comma I. I is not the I here. I is the identity matrix. Such that P is in P equal to Q0. Sorry, P Q0 comma I. Let's write Q0 comma. What will be final state? Okay, for final state, that's what I thought that I forgot something. Okay. You get this. So delta power W of gives you this. Now, given I, set of initial states, okay, I can represent I as a column vector of size 1 cross q. And F as a column, this is a raw vector, and F as a column vector, q cross 1. Okay, or rather F transpose. F transpose will be this column vector. It's just the characteristic vector of the initial state. It says that there is a 1 if that is in the initial state. There is a 0 if it is not in the initial state. So given any state, any subset, you can represent it as a characteristic vector, right? This is not, you don't need any linear algebra here. It's just very simple. F transpose. Now, what will be I times delta W dot F transpose? I multiply I delta power W followed by again F transpose. What will be that? What do you think that is? First of all, let's find out what is I times delta power W. It has a 1, so what is its dimension going to be? I times delta power W, what is its dimension? 1 power q, right? Because the delta power W is a q cross q, I is a 1 power q, 1 cross q, so delta power W, I dot 1 delta power W will be 1 cross q, and it will have a 1 if, it will have a 1 if,
No, you would have a this I dot delta W delta W dot F transpose. It would be 1 there is a basically it got it.
yes, but is that clear to everybody? You multiply those things together, and so this is 1 cross q times q cross q will be 1 cross q, again times q cross q will be 1, so it will give you just one value, okay? It will give you just one value equal to 1 if I P A equal to 1. Okay. Now you need to decode that and tell me what is going on. So A is the Boolean matrix, just arbitrary Boolean matrix. Q0 comma I, where Q0 is the initial state, I is the identity matrix. F is the final state, which is P comma A, where such that if you consider IP, what is IP? IP is a characteristic vector of the state P, okay? State P. If you consider P as the initial state, IP A F transpose will be 1, is what I claim. So let's see what happens here actually. So initially you have Q0 comma I, right? Initially you have Q0 comma I. After you read QA1, what is it going to be? It's going to be Q comma delta, okay? Such that on Q0 on A there is a run, on A there is a A1 there is a run. And after you read A2, it will be Q prime, so this is Q prime and this is Q double prime, comma delta square. Is it clear? Because transition just multiplies by delta square, okay? Delta square. Again on A3, it will be Q delta cube and so on. But you know that whatever, how many ever you multiply, there are only finitely many matrices. So this is eminently a finite state automaton, okay? So what is going on? At the end when you reach Qn, comma, delta power n, what you check here? What does this collect? Delta power n. Yeah? Paths of length at most, paths of length exactly n, right? So at any point of time, what you are collecting is set of states which has a path of length that much. But you know that there are not infinitely many such matrices. So, no, it's not clear. So till which point you understood?
Try to fit it with that half part. This for half step.
Okay. Okay, so what is the length of this string? This string is an. Okay. Now let's see, for the time being, let's forget about the matrices, number of matrices being finite. Let's see what is going on here. On the left position, on the left first component, you have a run from Q0 to Qn. That's clear. So it's going on fine. On the right hand side, what is going on? You are just multiplying by delta. Initially you have the identity matrix, you are multiplying by delta. Delta, delta, cube, delta, delta power n. And I say that now what is delta power n? Delta power n has an entry 1 if and only if it has an accepting run of length n, right? Now I claim that my final state is where you reach a state p such that from, you know that from this means that from p there is an accepting run of length n. Now you have to ask questions and only I can explain properly. You understood? Did you understand? No, you can ask me if you didn't understand. It's a very simple idea, but it's just that you may not be familiar with this representation of inertial automata, that's all. Should I explain once more? Okay. That's for half of n. What about 2 power x? Now I claim that all I need to change here is a goes to a square. That will be log. That will be log. Why? Yes, because initially it is initial state. Okay, then in that case it has to be delta. Okay. Delta square, delta power 2 power 2, delta power 2 power n. Okay. In all these cases, what is saving us is the fact that there are only finitely such matrices, right? Because we are not actually bookkeeping everything, right? We are not bookkeeping everything. What we are saying is that at some point we will confuse. You can find some kind of pendulum. At some point we will confuse delta I with some delta j, but that is okay. As far as we know that we have a run, because all it says is exists a y. Yeah. 2 power y mod x. Yeah. Yeah, in this case it will be just y. Yeah. Yes. Yeah, so in all these cases you can just say it as y. But it is also correct that oh no, sorry. It's not. Sorry. Yeah. And you can also think that it's x dot y, because if you change that p to q0 again, if you change that p to q0, what will be it? Instead of p, IP to IQ0. I claim that X will be such a string that there is some string, not necessarily a prefix of, not necessarily of which X is a prefix. X will be accepted if there is some string which is accepted whose length is exactly exponential of X, right? Yeah. Yes. Yeah, so in all these cases it is going to be X. Yeah, it's going to be X. It's just going to be Y. But you can also find that it's, yeah. What about square root? This is a, okay, let's do Fibonacci first. Okay, this is for this one. And for Fibonacci, what do I do? Can I rub this? So for Fibonacci, what I do is, I'll say that Q times MQQ times MQQ. Okay? And set of states will be, and P comma C comma D will go to P comma. So this is, suppose this is F n minus 1 and this is Fn. In that case, Fn plus 1 will be this times this. D comma. Is it correct? Yeah. Yeah. What did I do here? I know that this, so I need pass two lengths. Pass two lengths. Okay. So initially, what is my initial state? Initial state will be Q0 I comma I. Okay. Because Fibonacci starts with 1 1 1 1, things like that, right? I comma I. These are identity matrices. And now at any point of time, okay, you can again write that same figure. Huh? Let's write that figure. So you have A1, A2, A3 up to AN, right? Initially you start with Q0 identity matrices. What is the property? All the time you have to remember that this means that there is a length of, path of length 2, right? So this is the case. No, there is D delta. No, sorry. 1 second. Huh? Yeah, I comma delta. Because this is a path of length 0 and this is a path of length 1. Right? Fibonacci starts with like that. The initial first term is 0, second term is 1, then 1 plus 0 is 1 again, 1 plus 1 again. Okay, so what do we compute here? After reading A1, we'll go to some Q prime and I will go to delta. Delta will go to delta. After this, we will go to Q double prime. Delta will go to delta and this will go to delta square. Right? You just keep on multiplying. So this in terms, in a sense, tells you that, you know, any recurrence relation can be computed. In paths of length, any recurrence relation can be computed. I think it's not very clear, but since you understood the idea, you can reconstruct all this stuff. What time is it? Yeah, so it's 10:35. And let's leave these things for your exercise, square root. In this case, make use of the fact that n square, n plus 1 square is same as n square plus 2n plus 1, right? So at every point of time you have to keep track of the square, the currently computed value, then this term 2 delta, and then identity matrix. Identity matrix you can get at any, delta you can get at any time. So make use of this. So that's the idea. In general, this can be summarized into a theorem. Okay, maybe with that I will conclude. This is true. It is true that. So let me just introduce this concept also, and then I'll finish. You know what is a periodic set? Suppose you have a set A subset of n, A subset of natural numbers. You will say that A is periodic with period P when M is in A if and only if M plus P in A, right? So you have this if you have this, right? So this is a periodic set with period P. You will say that A is eventually periodic if there is an M such that for all n greater than M, n is in A if and only if n plus P is in A. That means when you start, it's going like this, but then it's after some point it starts being periodic. So you have a finite prefix, and after that it's periodic. A small observation, then I'll state why. How do you actually? So I say that. So you have a language L. Language L. You see, you defined lengths of L as the length of all W, such that W is in L. Okay. Now I say that for regular languages, lengths of A is eventually periodic. And how do we prove this? It's very easy. It's actually a manifestation of pumping lemma, right? Because if you have a sufficiently long word, you can just pump it, and you can get this. Let's do it for when sigma equal to 1, size of sigma equal to 1, when your alphabet is unary. Then I claim that any deterministic finite state automata will look like this for over sigma. It will start off like this, and then it can't go on forever. It has to fall back onto itself. Right? So any deterministic finite state automata over a unary alphabet will look like this. It will have a tail, then a loop. Why? Why is it the case? Over a unary alphabet, any deterministic finite state automata will look like this. It have a tail and then a loop. Okay, number of states is finite, that's why you fall onto itself. But why this particular form? Why can't it branch off from here? Yeah, because the alphabet size is 1. Alphabet size is 1, so it has to follow like this, right? It will look like this, and this is a periodic set. Why? Because this will be the initial M, and this will be the period P, right? This will be the initial length M, and this. Now I claim that for any, this theorem is true. Why? Because given any finite state, any language L, what can I do? I can take that finite state automata, deterministic finite state automata, make every label A, every label in that automata A. Now I don't change the lengths of any string, right? The lengths are preserved, right? Because earlier if there was a path, now also there is a path, except that this thing has changed, right? Hence, I can conclude that automata, the length in lengths of words in that automata is same as length of words in this automata. Hence it is also eventually periodic. Is the argument clear? Right? No. I want to say that for every regular language L, you understood what is length of L. Length of L is length of all the strings in that language. Okay. So for instance, A star, B star, the length will be entire set. Right? Entire set. AA square, AA star will be even numbers. Right? AAA star will be odd numbers. Right? Intersection of AA star and AA star will be what? Intersection of AA star, intersection AAA star will be what? Multiples of 6. Right? So in this case the lengths of this language will be multiples of 6. In this case it will be multiples of 2. In this case multiples of 3 and so on. Now I say that for any regular language the length is eventually periodic in the sense that it will have an initial fluctuations and after that it is a periodic function. Right? If there is a length of say 12 then there is, and the period is 5, then there is a length of string 15, 17 and so on. Now how do I prove this? So for proving this I observe that for our unary alphabet the automata looks like this. Now given any regular language L, I have a automata for that. I have a deterministic finite state automata for that. I take that automata, replace every label by a single letter A. I claim that the length of strings hasn't changed. Why? Because earlier if I had a path of length n, now also I have a path of length n, except that I have replaced everything by A. And since this is our unary alphabet, I know that it is equivalent to something of this form, because now it has become non-deterministic. Right? When I replace the labels, it has become non-deterministic. Now when I determinize it, I'll get something of this form. This is a M and a period P, hence this is eventually periodic. In the sense that, and it has another name. It has another name in logic. It is called semilinear. All this stuff. But anyway, and the general theorem for this thing will say that any function which preserves periodicity, eventually periodicity, will actually, and any function for any function f which preserves eventual periodicity, if you define this string, if you define this thing, it will be periodic. But it's not a very hard theorem, it's very easy. But even if I prove it today, you will forget. Yeah, and the origins of this problem, Ginzburg asked this question in 1962. Ginzburg was a automata theorist and a concurrency theorist, and he asked this question whether, so hence this is called the classical half problem, half of a language problem. He couldn't solve it, but we know that how simple this is. And this theory, it's not, we are on the verge of getting into automata, because these matrices form a semi-ring, because Boolean matrices does not have inverses, right? You can verify that, Boolean matrices may not have inverses unless there is exactly one in every row and every column. Okay? So these matrices does not have inverses actually. So they don't actually form a ring, unlike general matrices. General matrices, if you restrict to matrices of determinant 1 or non-zero, you will get a ring. But they don't form a ring, so they will form a semi-ring. That means the additive, this thing is not a group, but it's a semi-group. And hence this theory just picks off from there, and it gets into semi-rings and so on. But for all these things you don't need any more than just basic observations, like when you multiply. So that's the same idea of Floyd-Warshall algorithm. Floyd-Warshall algorithm can also be used for finding transitive closure, right? You will do the same thing. You have a Boolean matrix, and for every row, every column, it's actually multiplying it again and again. Any questions? Any general questions?